Hello everyone, this is Ifshit Ibn Idris. I am a PhD student in the Department of Construction Management at LSU. Today I am going to present our paper titled as Variability and Uncertainty of Overlay Tester Testing Data Analysis and Results. Okay, let's begin. Outline of the presentation is shown in this slide. The presentation will begin with a brief introduction followed by the objectives and background of the study. Then, the sources of variability in the overlay tester testing procedures, along with the factors affecting variability in the overlay tester data analysis, will be discussed. And finally, the summary and the conclusions will be mentioned. Reflective cracking is a common phenomenon that occurs in flexible pavements constructed over stabilized bases. When the existing base has severe cracks in its surface, the effect of traffic loading and seasonal temperature variation causes these cracks to propagate upward, and these cracks demonstrate the same pattern as the cracks in the base coats and thereby referred to as reflective cracking. There are two types of reflective cracking as shown in this figure here: double reflective cracking and single reflective cracking. However, double reflective cracking occurs mostly in semi-rigid pavements and can rarely be found in flexible pavements, and therefore our focus of this study will be on the more frequent and more complex traditional single reflective cracking. Although zero reflective cracks are cosmetic in nature, wide reflective cracks having a crack width greater than 6 mm can cause various structural and performance related problems as listed in this slide. So, as mentioned earlier, wide reflective cracks can cause various structural and performance related problems for the pavement structure. It might be a major concern when selecting asphalt mixture surface courses with stabilized bases, or when there are severe surface cracks in the current pavement structure. Researchers worldwide have developed various laboratory testing devices that can simulate mechanisms of reflective cracking in the laboratory, as shown here. However, it is very crucial to identify the most reliable laboratory testing equipment to study reflective cracking in the laboratory. Overlay tester, developed by the Texas Transportation Institute, shown here in this figure, is a widely used tool to study thermally induced reflective cracking in the laboratory. This device is famous for its commercial availability, simple specimen preparation procedure, simple testing procedure, quick testing period, availability of the standard test method EX248F, and easy data analysis procedure. However, like other devices, this device also has some limitations, and the most critical one is the high variability associated with the test data, more specifically, the high variability in the number of cycles to failure. And sometimes the coefficient of variation is over than 40%, which is not acceptable. Objectives of the study are listed in this slide, which include identifying and categorizing the sources of variability in overlay tester testing, data analysis and results, and providing recommendations to improve the repeatability of the overlay tester testing data. Now let's talk about the overlay tester and its testing protocol. The upgraded T&DI overlay tester consists of two aluminum or steel base plates over which the specimen is mounted, as shown in this figure. One base plate is stationary while the other can slide horizontally or vertically. The base plates are placed 2 mm apart to represent a crack or joint in the base, as you can see here. The device can test both laboratory molded and field course in accordance with EX248F. The standard dimensions of the prepared OT specimen is shown here. A standard OT specimen has a diameter of 6 inches, has a width of 3 inches, and has a height of 1.5 inches, and the specimens are glued over the base plates using epoxy. The testing in OT is typically conducted at room temperature, which is 25°C, and the specimens are tested under a displacement controlled one-phase loading, as you can see here. It has a standard maximum opening displacement of 0.63 mm. Throughout the testing period, the time, the displacement, load, and the number of cycles to failure are measured. Failure criteria that is defined in the test standard is a 93% reduction of the maximum load, with the load measured in the first cycle or 1000 loading cycles, whichever comes first. Sources of variability in OT testing procedures. The inconsistencies in OT results have always been a matter of concern, which raised questions about the repeatability of the test procedure among the researchers. Considerable efforts have been made by the researchers to understand the sources of high variability in OT results, more specifically in the number of cycles to failure. Garcia et al. Noted that the high variability of the number of cycles to failure might be attributed to the precision of the load cell used in the OT machine as shown in this figure. Load cells that are commonly installed in the overlay tester have capacities of either 5,000 or 2,000 pound with a precision of 0.1%. The reported loads are within 2 to 5 pound of the actual values. When a 93% reduction of the peak load occurs, the level of uncertainty in the measured load can be up to 10% of the actual value. Therefore, the precision of the load cell has the potential to introduce a significant variability to calculate the number of cycles to failure consistently using the current failure criterion. Another source of high variability in the number of cycles to failure might be attributed to the complete non-adherence to the standard test procedure, which is EX48F. In this study, an attempt has been made to identify and list the potential sources of variability in overlay tester testing procedures. The sources are listed in this slide. Walovitha et al. Evaluated the effect of drying method on the overlay tester number of cycles to failure, and it was concluded that oven drying of the specimens resulted in more uniform drying of the specimens and provided with more repeatable results as compared to air drying. Walovitha et al. And Garcia and Miramontes evaluated the effect of sample seating time on the number of cycles to failure. Although Garcia and Miramontes concluded that they found no effect of sample seating time on the test variability, Walovitha et al. Recommended that the specimens after preparation and molding should be tested within 5 days of molding to avoid the effect of aging the specimens. Walovitha et al. Evaluated the effect of air voids on the number of cycles to failure and concluded that an air void of 7 plus minus 0.5% yielded the most repeatable results. Moreover, Walovitha et al. Evaluated the effect of temperature variation on the number of cycles to failure, and he concluded that no trend was observed with respect to variability due to temperature variation. More details can be found in the submitted paper. Walovitha et al. Examined the effect of glue type on the number of cycles to failure. They evaluated three different types of glues, namely Devcon plastic 5 minutes epoxy putty, Devcon high strength epoxy, Devcon 2-part two-tone epoxy S31. And they concluded that the two-part two-tone epoxy is the best overall choice with regards to performance, economy, workability, and consistency. Walovitha et al. And Garcia and Miramontes both examined the effect of plate gap width on the OT test results. Garcia and Miramontes concluded that the effect of gap spacing must be examined further as their results were inconclusive. On the other hand, Walovitha et al. Recommended that 6.25 millimeter gap plates should be used. However, the repeatability was similar for both. Walovitha et al. Further examined the effect of glue quantity on the test results. They used three different quantities of glues, which were 14 gram, 16 gram, and 18 gram. And then the results showed that 16 gram two-part epoxy per specimen was found to be providing most consistent testing results. Walovitha et al. Further evaluated the effect of number of replicates uh, on the OT test results, and they recommended that need to test 5 specimens and we can pick the best 3 from them with the lowest coefficient of variation. Garcia and Miramontes evaluated the effect of glue curing time on the overlay tester results, and it was found that the gluing time should be between 12 to 24 hours to allow the glue time to cure properly. Garcia et al. Further examined the effect of glue strength on the overlay tester testing results, and it was recommended that 4400 psi or stronger glue should be used to minimize the failure of the bond between the specimen and the plates. Garcia et al. Also evaluated the effect of the weight on top of the specimen while curing. They found that 5-pound weight should be used while curing to reduce the amount of glue squeezed out of the sides and maximize the thickness of the glue. Finally, Garcia et al. Proposed a new gluing method and compared the test results with the 2009 version of the gluing method, and it was concluded that the proposed method should be used as it decreases the variability to a great deal. Now let's talk about the factors that might affect the variability in OT data analysis. Garcia et al. Proposed a novel methodology for interpreting overlay tester raw data. It was found that the hysteresis behavior of the specimens in the first cycles was almost entirely different from the hysteresis loops of the remaining load cycles. Additionally, the first hysteresis loops were almost identical for different mixtures as shown in this figure. Therefore, it was indicated that it is more feasible to characterize different specimens using the first hysteresis loops instead of considering all loops, and the damage during the first cycle might be an essential indicator of how the mixture performs the rest of the test. Therefore, rather than using number of cycles to failure as a performance index for reflective tracking, Garcia et al. Proposed that the raw data should be analyzed and reported by 2 different parameters independently, reporting resistance to crack initiation and propagation, and those 2 factors are critical fracture energy and crack progression rate, also known as GC and CPR respectively. Garcia et al. Defined GC as the energy needed to initiate a crack in the specimen bottom at the first loading cycles, which was calculated from the area under the hysteresis loop of the first loading cycle as shown here. A higher GC value indicates that the asphalt mixture will need higher energy to initiate the crack and will exhibit greater resistance to reflective cracking. On the other hand, CPR was defined as a surrogate parameter that characterizes the flexibility and fatigue properties of the specimens during the crack propagation phase. It was calculated by fitting a power equation as shown in this figure, the normalized load reduction curve, where the absolute value of the power term B is always negative, and thereby referred to as CPR. A higher value of the CPR indicated faster crack propagation through the asphalt mixture specimen and exhibited shorter fatigue lives and vice versa. Garcia et al. Evaluated the variability of the 2 new parameters, critical fracture energy and crack progression rate, otherwise known as GC and CPR respectively, through a multi-laboratory study conducted by Texas Department of Transportation and the University of Texas El Paso using a dense graded Type-C mix. It was found that GC and CPR showed acceptable variability among the results from the 2 laboratories. Additionally, in addition to GC and CPR, a new parameter referred to as corrected crack progression rate or CCPR was proposed by Garcia et al. Considering the viscoelastic nature of the asphalt mixtures. The proposed CCPR parameter exhibited satisfactorily lower variability as compared with CPR. And finally, Garcia et al. Set the preliminary acceptance limits for these 2 parameters, GC and CPR. More details can be found in the submitted paper. Conclusions and recommendations. After measuring the air voids, overlay tester specimens should be oven dried to ensure uniform drying rather than air drying. Overlay tester specimens should sit for a maximum of 5 days between molding and testing. Air void percentage of 7 plus minus 0.5% is acceptable. 16 gram of glue per overlay tester specimen should be used to maximize the repeatability. 2-part two-tone epoxy should be used to minimize the failure of the bond between the specimen and the overlay tester plates. Epoxy should be allowed to cure for 12 to 24 hours to ensure proper bonding between overlay tester specimen and base plates. A 5-pound weight should be used during curing to maximize the thickness of the glue layer, and parameters of GC, CPR and CCPR provided improved repeatability as compared with number of cycles to failure and should be further explored in future research. These are the part of the references that were used in the study. Thank you very much for your time and attention. If you have any questions, feel free to ask me and I will be more than happy to answer. Thank you.